Welcome, students. Today, we're jumping right into a complete explainer on foundational electrical circuit theorems. Whether you're a first-year B.Tech student, doing your Polytechnic Diploma, or gearing up for competitive exams like GATE, getting these concepts crystal clear is absolutely crucial. We're going to break down exactly how circuits behave, decode the mathematical proofs, and give you the practical tools you need to tackle complex numericals with total confidence. So let's get started.
Okay, here's a quick look at our agenda for today. First, we'll cover the linearity property. Second, the superposition theorem. Third, Thevenin's theorem. Fourth, the Norton equivalent. And finally, we'll wrap up with time domain analysis for RL and RC circuits.
Right, section 1. Linearity. The core principle. Let's get into it.
So before we can solve massive electrical networks, we absolutely must understand linearity. For linear elements, like your basic resistors, the relationship between cause and effect is perfectly proportional. This really boils down to two things: homogeneity and additivity. Think about the electric room heater or the iron in your house. If you double the input current, the output voltage across that heating element's resistance exactly doubles too. That's homogeneity. Additivity just means that if you have multiple sources, the total response is simply the sum of what each source does completely on its own.
And Ohm's law is the perfect proof of this additivity property. Notice how if we apply a sum of two currents, say I1 and I2, we directly get the sum of their individual voltage responses, V1 plus V2. The math literally proves that a simple resistor is a perfectly linear element. There's no magic here, just straightforward proportions. Moving on to section 2, the superposition theorem demystified. Now, this brings us to a massively important topic for your university exams: superposition. Listen carefully, because the golden rule here is that when you analyze one independent source, you have to completely deactivate all the others. To turn off an ideal voltage source, you short-circuit it. Just imagine replacing that battery with a plain straight wire. For an ideal current source, you open-circuit it, completely breaking the path. But here is a massive exam tip for you. Leave those dependent sources alone. Never, ever turn off a dependent source because they completely rely on other variables inside the circuit to function.
So how do we actually use this in an exam? Just follow a very systematic four-step method. Consider one independent source at a time, deactivate the rest, calculate the current or voltage in your target branch, and then algebraically sum up all those individual responses. Whenever you face a numerical problem with multiple independent sources, superposition should be the very first tool that jumps into your mind.
But as any experienced engineer will tell you, this theorem is not a magic wand. Applying superposition to a massive circuit with dozens of sources, that quickly becomes a very painful, tedious experience. Plus, it completely fails the moment you introduce nonlinear elements like diodes or transistors. And here's the biggest trap students fall into. You absolutely cannot use superposition to calculate total power directly. Let me show you exactly why.
Let's completely prove why power calculations fail here. Imagine a circuit where two 12-volt batteries are directly opposing each other. If you blindly used superposition to calculate power, you'd find 12 watts from the left source, 12 watts from the right source, and you'd probably guess a total of 24 watts. But wait, in reality, those opposing batteries cancel each other out completely. The actual current flowing through the resistor is zero, which means the true power consumed is zero. Since power relates to the square of current or voltage, it is mathematically a nonlinear operation. Superposition and power just do not mix.
Okay, let's move to section 3, simplifying with Thevenin's theorem.
Because superposition can get really tedious, we use Thevenin's theorem to simplify our lives. In real-world engineering, we constantly deal with a fixed circuit connected to a variable load. Think of a standard household plug point. You might plug in a fan today, a heater tomorrow, or a mobile power bank the next day. Instead of recalculating the entire internal wiring every single time you change the load, Thevenin lets us condense the whole fixed part of the circuit into just one equivalent voltage source, V Thevenin, in series with one equivalent resistor, R Thevenin. It is a total game changer.
I want you to keep this core concept locked in your mind. We are essentially taking that complex, fixed part of the circuit and stuffing it into a simple black box. From the perspective of the load terminals, this simplified black box behaves exactly, identically to the original messy network. It makes solving complex numericals so incredibly efficient.
All right, section 4, the Norton equivalent circuit. Let's see the other side of the coin. Developed independently back in 1926 by Mayer and Norton, this theorem is basically the mirror image of Thevenin. While Thevenin uses an open circuit voltage in series with a resistor, Norton completely flips the script. It represents that exact same complex network using a short circuit current, the Norton current, running in parallel with an equivalent resistance. And here is a fantastic time-saving shortcut for your exams. The Norton equivalent resistance is the exact same value as the Thevenin equivalent resistance. You calculate it the exact same way. If you strictly execute these specific steps, shorting the load terminals to find your Norton current, turning off the sources to find your internal resistance, and drawing them in parallel, you can transform any messy spider web of linear DC components into a neat, highly predictable current divider circuit. Reconnect your load, use the simple current divider rule, and boom, you have your answer.
Okay, let's dive into our final module today. Section 5, Time Domain Analysis for RL and RC Circuits. We are now shifting gears from static DC analysis to watching how circuits actually behave over time when switches are thrown. This is the whole concept of transients. To nail first-order transient problems, understanding these initial and final states is your ultimate cheat sheet. You absolutely must memorize this. Remember the core rules. An inductor stubbornly opposes any instantaneous change in current. So the precise moment a switch closes, it acts like an open circuit. A capacitor, on the flip side, fights sudden changes in voltage, initially acting as a complete short circuit.
Let's visualize this with a real-world setup. Imagine a switch connecting a battery to an inductor. When you first close that switch, right at time t equals 0 plus, the inductor strictly fights the current, effectively acting just like an open circuit. But if you wait long enough to reach what we call the steady state at time infinity, that transient period is over, and the inductor gives up the fight. It behaves just like a simple, plain piece of wire, a complete short circuit.
Now, listen up, because this is the absolute secret shortcut to scoring top marks in your university exams. Whether you're solving for a capacitor's voltage or an inductor's current, you don't always need to grind through massive, scary differential equations. Just use this universal shortcut equation. Your total solution is simply the final steady-state value plus the initial value minus the final value, all multiplied by e raised to the power of negative t divided by the time constant t. This one elegant formula seamlessly blends the forced response and the source-free response together. So your methodology becomes incredibly systematic. Find your initial conditions, find your final conditions, calculate your time constant, which is just R times C for capacitors, or L divided by R for inductors, and then plug the whole shebang right into that formula. Doing this yields a beautiful mathematical decay function, perfectly showing the current dropping off exponentially over time. It really is that straightforward.
We've covered a tremendous amount of ground today, mastering the essential toolkit for linear passive circuits. We've seen exactly how superposition, Thevenin, and Norton can drastically simplify our lives, and how time domain equations decode transient states. But before we wrap up this explainer, I want to leave you with a provocative thought to ponder for your future studies. What exactly happens to our pristine symmetry and all these neat superposition rules when we step out of basic DC networks and introduce complex AC admittance matrices and active dependent sources? How do the rules of the game change then? Keep practicing those numericals, keep strengthening your concepts, and I'll catch you in the next explainer.